Hi there, so this is my review of my part 2 of lecture 22 review of diagonalizing matrix. So let's discuss the next one, which are the 4 remarks that is stated in the book, which I think is also important, and particularly this one, the last one, the diagonalizable criteria. So first one is the undistinct eigenvalues have undistinct eigenvector as well. So that simply means if I have a matrix A, let's give it a 3 by 3, and then I have a lambda 1, lambda 2, lambda 3, and they are all distinct. They are not repeated. So no repeating eigenvalues. In other words, they are distinct. Then it is automatically means that I have also undistinct eigenvalues x1, and this is diagonalizable. That seems quite hard to pronounce, right? Diagonalizable. Okay, so just remember that the requirement for diagonalability is that undistinct eigenvalues, so therefore it has independent, so that word is also important actually, independent eigenvector. Yep, so please keep in mind that this rule exists. So undistinct eigenvalues automatically has undistinct eigenvector. Okay, now let's move on to the second one, that you can multiply the eigenvectors by any constant and this formula is still valid. So this is pretty simple. So you have this in the beginning, but you need to multiply this by some constant, non-zero constant, so this will be still valid. So C is not 0, right? So for example, what happens is if you have an eigenvector which is not in the unit vector, their length is not 1, then you want to normalize it. You divide it by the length so that they equal to 1. That still happens. That's actually what happened inside the MATLAB. The eigenvector will, when you want to compute the eigenvector, the MATLAB will always return the unit vector, the unit eigenvector, that's what I mean. So implicitly they did this multiplication by some constant there. Okay, and the third one is the same order. So what that means is, let me write it here. So the x1, x2, x3, so this is particularly useful when you're writing this form. So you want to write the eigenvectors matrix and the eigenvalue matrix. You have this lambda in the diagonal position. So what this means is that they have to be in the same order, which means here in the first column I have the first eigenvalue in my first column, and so on and so forth. So if you interested in like switching them, so let's say x2, x1, x3, so you need to also switch those to comply with the rule, to keep the rule valid. So you have lambda 2, lambda 1, lambda 3 there. Okay, so that's what it means by the same order. And the last one, the diagonalability. So let me clean this up a little bit. So previously I mentioned that when you have the distinct one, so lambda 1, lambda 2, so you automatically also have the distinct independent eigenvector x1 and x2. So in this case, the lambda 1 doesn't have to, it's different than the lambda 2. And now what happens, there's also a case where you have a same eigenvalues, so like this one. So in that case, you may or may not have a distinct eigenvector. Okay, so that's the case that we didn't discuss earlier, but I just want to mention a case where there is a same eigenvalues, a matrix has the same eigenvalues, could happen, and they could have the same eigenvector as well. So there's a condition of like we are lacking the eigenvector, lack of the independent eigenvector. Actually, that would be the correct way to say it. So let's run an example, right? So there is an example of triangular matrix, which is some sort of review as well. So in this case, it's really easy, right? The triangular matrix, how to determine the eigenvalue, you just have to do this, and it's there actually. A 2 by 2 triangular matrix is always the best, because you know this lambda 1 is 3, lambda 2 is 2, and they are distinct, therefore you have two independent eigenvector as well. But how about if I write it this way? Instead of 3, I have 2 here. And we did the usual A minus identity lambda, and then we have it in this form. So we now have lambda 1 of 2 and lambda 2 of 2. Okay, now let's say we continue this. Okay, we want to find the eigenvector. Now what does this evaluate to? So this will be 0 because the lambda is 2, and we will have this. So the eigenvector is some sort of like 1, 0. You can put any constant actually there in the first row, and the 0 combination of column 2, and then you get it in a null space. So this is it actually in the null space. But see, we only have this one line, you know, for these two eigenvalues. So in this condition, we don't have that independent eigenvector, right? Because we only have one. And actually, you can say that the second eigenvector is also this line. So they're not independent, of course. So in this case, our matrix A, so in this case, this A is not diagonalizable. I'm having a hard time writing that. So please keep that in mind. Thus, if this is the case, then all that we have been learning so far, that this formula right here, and also about writing it in terms of this, it also invalid. This won't happen. Actually, this thing can still happen, right? Because you have those eigenvector and you have those two identical eigenvalues, but this thing required the inverse of this eigenvector. So this won't happen. Therefore, so far we have been working with the assumption of the independent eigenvector and invertible eigenvector matrix. So keep that in mind. And a quick mention is that in the book there's also a term called GM and AM. So GM is the geometric multiplicity, and AM is algebraic multiplicity. I cannot write that down, obviously. Anyway, the rule is that the AM has to be equal to GM, right? In order for the matrix to be diagonalizable. Like this case, if I have two eigenvalues, I need two independent eigenvector, 3 of them, and I need 3 of the eigenvectors as well. But in this case, we have, so let me tell you that geometric multiplicity refers to the number of independent eigenvector. So in this case, the GM is 1, while the algebraic multiplicity refers to the number of repeated eigenvalues here. So this is 2, so AM is 2. So here we have GM less than AM, therefore our matrix is not diagonalizable. So that's it for part 2. See you in part 3.